John going up, a tremendous piece of structural engineering that we look forward to see the testing side. So what I'm going to do here, I'm just going to give you divide the talk in two parts. Can you hear me at the back? Yeah. Is that okay at the back? Yeah. Okay, so I'm going to divide in two parts. I'm just going to give you a very brief set of slides on once I get gray here, what do you think should be doing perhaps impacting our practice of structural engineering. And then I'll go and review two projects. Both projects were under the NHERI umbrella as opposed to the NHERI umbrella. One is mainly having a direct impact on society and in industry, and the other one more transformational. And with those ones, we open up for questions later on. We will have questions at the end, right? So let's begin. So let me talk about the first part. I had the opportunity in 2019 to go and work in Lombok. It's an island east of Bali, small island, fairly volcanic. And if you look in 2018, that island had 1, 2, 3, 4, 5 large magnitude earthquakes that significantly impacted the society there. Of course, if we look at papers, we see Lombok and we see the damages. So, but the other thing is to see, go a year after the last earthquake of them all, and you see people still living on the streets. So basically their houses collapse and the mattresses are pretty much on a shack, you know. And if it rains there, it's the tropics, it rains there. So one of the things that we see as part of, in my area of structural engineering, obviously it should have a direct impact in society. It shouldn't be, in my opinion, to satisfy your own ego, but just to see how can you impact and look 20 years after and see how has your work impacted society. So if you go to places in Lombok, you see some of the mosques, new mosques completely destroyed. It's an island that wanted to get some tourism spilling over Bali, but then all the marine structures were completely destroyed by the earthquake. They had just recently built an arts center for tourism as well, and you see the non-structural components affected, and the building basically is unusable. And finally, Indonesia in 2004 experienced significant earthquake and tsunami, so they went to these islands and started to build tsunami refugees with high floors. You can see these guys here. Well, this guy didn't get to the tsunami. It was substantially damaging these earthquakes. So when you add all these things up, you see in the end who is having the impact. The people, the normal people. So if one of the things I think when I try to put forward research is see how are people going to be impacted, not only in the United States, but hopefully go somewhere in places where you can have, with some minimal effort, you can have a good impact in somebody else's life. So now, when we look now into what we're doing with experimental research, so we can do a lot of analysis these days, but if we look back and we see now we are shifting from testing components, something that we were doing 20 years ago, 30 years ago, a lot of component testing, but now the new facilities that we have under, initially under the NHERI, now under the NHERI umbrella, are allowing to do way more complex type of testing that are supporting analytical work. So now we can look into system behavior and system interactions. So it's moving away from the component, but now look at system interactions. We can now look at all the vulnerable systems and find ways how to retrofit some of these systems, some with very simple methods. And I can think, for example, of the work that Professor Marcial Blondet does in Peru with a small shaking table. In Peru, many of the indigenous population can live at 4,000 meters, that's 12,000 feet, freezing every day, and they live in earthen houses. Now you have earthquakes, they come down, and he's been able to do simple geosynthetics mesh to confine these houses and to offer significant protection. So all these things are incredible when you go and see what is the impact at the end of the day of the research. Low damage is something that you guys saw today in the building being put in place for the building, for the 10-story building that we have, and I will talk about a little bit about these. We also have protective systems and smart systems. Base isolation has been since 1981 in place in New Zealand, and it took a while for it to emerge somewhere else, and now we go to places like Japan, Chile, back to New Zealand, and now we see a widespread use of seismic isolation, and there will be a significant use of seismic isolation here once we are hit by a significant earthquake. Why? Because we still have the inertia that not much has happened with the traditional systems, but there will be a time to change, like they did in all these countries. You go to Ecuador, Peru, all of them are now making use of seismic isolation. We look into non-structural components and contents. Non-structural components are difficult. You don't make two of them the same. And yet they seem to experience a lot of damage in earthquakes, and they cost a lot of money and downtime. Working in sensors and monitoring systems, we now see advancements. Professor Hutchinson and her group are working now in basically sensing via drones, and there are groups working with very interesting results in this topic. Risk assessment and hazard mitigation, multi-hazard, multi-scale investigations. And last but not least, model calibration. And that's a very interesting one that I would like you to take serious notice when you write a proposal. We think we are good. We think our models are wonderful, you know? But the reality is when we do blind predictions, and that's what I would like you to encourage you to do when you write a proposal, put a little pocket of money to do blind predictions. Encourage the practice to do blind predictions. It is fascinating what they learn, what you learn, and it's eye-opening when we see how far are we. As a professor in geotechnical engineering once said, as he said, I thought that in geotechnical engineering we have such degree of uncertainty in our models, but actually we are there. Now, we are now worldwide in countries like Philippines, Indonesia, high seismic, Taiwan, you know, China, and India, in some parts of Gujarat, United States. We're going high-rise these days, Mexico City. And there is a lot to learn for these buildings. Now, with significant number of high-rise buildings in seismic regions, there is a lack of knowledge in the area. Damping, Professor Conte mentioned damping is one in solid structure interaction. Professor Bartenberg is going to talk about it. There are many things we don't know. And one of the things we think is, it was revealed in the Christchurch earthquake in February of 2011, is once we have a tall building that is damaged, what do we do? The city of Christchurch was cordoned off 18 months with a building leaning 1 meter. It bursted walls. And nobody was prepared what to do with these buildings. So these buildings were eventually demolished. And by the time the downtown Christchurch opened, the business had moved away from the city or moved away to the outskirts. And you go today to Christchurch, 11 years after the earthquake, and downtown Christchurch is a ghost city. It's interesting to think what are the consequences of damage of a big tower like this. And it could be the core wall that is being damaged, it could be that the diaphragms have been damaged and are difficult, if not impossible, to repair. Modeling, of course, we are very proud and we think we can do everything these days in the computer. It's a model we developed for the collapse of the automobile building in Chile, where 8 people died in this tragic collapse. And we see the degree of complexity. This is actually about 500,000 degrees of freedom in this old building, no linear analysis. And you can see how difficult it is. We just need to know what triggered the collapse of this building, and there are areas, for example, that we believe we never accounted for, and most likely one day we may be able to account for the rotational components in the ground motion. This building is somewhat slender, and a little bit of rotational components may have influenced the collapse of this building. And that's the real concern. So those are areas that can be explored. I had mentioned to you about the accuracy in our models. You look, this is the closest we get to a single degree of freedom. We can have a big lump, 250 tons of concrete at the top. We just cannot make it smaller. It's concrete. And it's all down there. It has essentially, in the direction we are testing, it has 3 degrees of freedom. The main one, translation, and a second one, which is rotational because of the rotational mass, and a vertical one because the column grows as we move laterally, but that's not anymore. Now, you develop a blind prediction. We did this through Peer, and man, it's a single degree of freedom. It's the simple circular column with bars here and there. Can we predict the response of that column? And it's an eye opener, you know. It's remove some of that that have wrong models, so remove the outliers at the top and the bottom. For one or another reason, the DHA can what's wrong. But look at the spread around the values that of the experiment. Look at this at the very beginning. Even essentially linear behavior in the reinforcing steel. Obviously, the column has cracked. Now we begin to have some uncertainty in the displacement demand. This is the horizontal displacement or lateral displacement in the column, and this is the earthquake number 1, 2, 3, 4, 5, 6. They were all of increased intensity except 4, which we basically reduced the intensity to see what happens. So these are the winners. The winners are not doing that bad, but there is significant scatter between winners and what we measure. Anything we can do to talk about damping, to talk about nonlinear behavior, to encourage the practical engineer to take the latest tool is an improvement that everyone can do. In your own area, in my area, reinforced concrete, but you can do it in your own area as well. But this is a serious question mark for us to bring people across the practice and try to reduce the degree of spreading the response.
Time-lapse footage reveals how the
Finally, I can see if I can stop this.
eerily recreates the earthquake.
Let me go back. So I say in 1999, or in the 90s, mid-90s, NSF funded a project called PRESS, P-R-E-S-S-S. And in this project, it was mainly, there were several universities, but University of Minnesota, University of Washington, and UCSD were key components here working with industry PCI on topics that were very relevant for the precast concrete industry. The precast concrete industry was seen as a bunch of cowboys that they produce something that always collapses in an earthquake. So in this project, they came up with some very interesting systems that are what we call these day low damage. They were post-tension pieces that rock and recenter with very little damage. So this is Nigel Christie himself showing the testing, the pseudodynamic testing that was done here at UCSD back in 1999.
Time-lapse footage reveals how the pseudodynamic testing process eerily recreates the earthquake.
But you're supposed to, without anything bad happening.
Susan Nakaki from University of Washington.
The lack of damage is surprising. It's been less than I expected. So it's just been great. Superb test.
The success of the PRESS program has been a defining event, which promises to propel seismic engineering, design, and science forward. What lies over the horizon?
It's always tempting to believe that we're just about finished what we need to do in earthquake engineering, but I suspect that people thought that in the 60s. The prediction was that there would be no more need for doing any testing in 10 years' time. Everything could be done by computers. 20 years after that, we started to build these large-scale testing facilities because we realized, in fact, we weren't getting the answers from the analytical models that were adequate. So I would hesitate to say that we're getting close to really understanding the way the structure of the neighborhood works. I think we're very much further on than we were 20, 30 years ago, but I think there's still plenty of opportunity for young research students and young faculty members to cut the teeth on their engineering problems.
A very bright mind. He passed away in December 2014, left us the legacy of low damage, and I think everyone has taken these in steel, concrete, precast concrete, and timber of mastic construction. So that's the way you want to benchmark and see if you can come up with a gear that will be long-lasting and perhaps transformational. So the part two of this talk is about some example projects. How do we tackle some of the projects in a different way? It is very humbling to see how a project of the complexity of the project that Lynn and his partners in this endeavor of the 10-story building has worked out. I mean, this is a high level of complexity of any project I have worked. Nevertheless, I will share some of the projects I have led here with some degrees of complexity and see how we have sorted them out and the reasoning for the project. So project number one is what we call the parking building, and this is what we call the parking building, and this is funded like many projects. And John was very explicit this morning in saying there is never enough money for these projects. You better partner with somebody. In this case, we have been successful interacting with the precast concrete industry, which is in a way my house. I worked in precast concrete for many, many years, and therefore it's an area where I feel very comfortable working with my peers and colleagues in the industry. So we had, these are multi-university projects with full of industry partners. Not only the precast concrete industry, but the precasters themselves and people who are support the precast concrete industry with connectors, EO connectors there. You add all these things up, and by the time you sum, your project funded by NSF was 1 unit, and you get the 3 units working with your colleagues. So always have in mind that if you want to if you start building a project from the low end, you can start doing some small projects, but then have somebody champion you in the industry, go to committees in your own area, whether it's geotech or whether it's steel or concrete or precast concrete. And start talking about this project, get to know your colleagues, and assemble that teammate that John mentioned this morning. The second one, this is impacting the precast concrete industry because of the damage experienced in the Northwich earthquake. The second one is more transformative in the sense that it can utilize some concepts in the IFAS project. Giorgio's work as a PhD student in this project, led several areas, Lehigh, at UCLB, Professor Chambers is now an assistant professor with us, and he's taking these concepts to level for utilization in those buildings. So your teammate, multi-university projects, it's not about you, it's about how I'm going to impact, and I'm going to be a team member or I'm going to be a leader, depending where you sit. You have the leadership skills, or you prefer to not to lead but contribute. That depends on the personality of every person. So in this case, we had an association of 3 friends. In our case, it's 3 friends, not 3 colleagues. There's Professor Richard Suss from Lehigh University, Professor Robert Flashman from University of Arizona, and myself here. Also at Lehigh University, we had Professor Clay Nato, who was an assistant professor then during that period. 3 professors. We don't do anything unless we have top students. So if you have those top students who are full of energy, who are really hungry to work, that makes the project a success. And you need to add also the technicals and support the staff that is going to be supporting all the testing you're going to do as well, in either Lehigh or UCLB. So we were looking here for full large-scale testing. The first proposal we had, we got an award from the Precast Concrete Institute. It was then $250,000, and we were going to do a little test on, like a capstone test on a shaking table. But we realized that the shaking table here was going to be available, and we say, oh, if we make it big, we can now use connectors that are at full scale or half a scale that can be made by industry and utilized, as opposed to a building kind of proprietary connectors that are not really the real thing. So by having the shaking table available here, we went back to NSF and to what we let's call a GOALI program. Then we obtained industry NSF funding to make this to build this project, and then we had all the funding coming from industry itself. Any project is associated with simulation, so we divided our task, and I'm going to show you how we divided this. There was testing done at Lehigh University with some components of analysis, testing done on the shaking table with components of analysis, and the University of Arizona, who was leading the project, they took the bulk of the analytical work. They did the detailed work, because that's where they didn't have the experimental facility. We involve significant design consultants that are our friends these days. I still talk to them on a regular basis. Design engineers, we just wanted to impact and see their opinions on what we do and what they want us to do, and tell them why it's not good, and they tell us why it's not good. So all these discussions take place in meetings that we do in several parts of the project. The topic here, floor diaphragms, they did not fare well in the Northridge earthquake. There was significant lack of knowledge on what a diaphragm is and how the inertial forces are transferred. These days, in fact, we still have, it's an obscure topic inside the design. How do we design a diaphragm? It's not quite clear to me how we are still tackling the design of diaphragms in industry. If we are 2022, and back then it was this idea of collectors did not even exist. So here is the testing done, part of the testing done at Lehigh University and the capstone project done at UC San Diego. This is an interesting test built at 40% scale. That's the team. We were young, you know. It's, life has changed my hair, but the color of my hair, and also Robert and Richard. So it's interesting to look back and always have this photo 20 years or nearly 20 years after. Okay, this is the problem. So this is the main issue. So we have these very large buildings with lateral systems, yeah, concentrated somewhere. And these guys develop inertial forces. How are you going to take the mass times acceleration through that diaphragm so it gets there to the lateral system? It's so simple to do it in the computer, just very simple. Do it in reality. It's difficult, it's challenging, it experiences many constraints, many constraints, and more if these precast diaphragms are precast, because you only have very little concrete to do it together, if not welding or so, which can have significant problems in the field. The result is the collapse, for example, of the shopping mall in Northridge, in the Northridge earthquake, where the lateral system stood in place with no problem and everywhere else went down. So when we, and I don't know how am I doing for time. I have 6 minutes, I'm going to go fast. There were very little knowledge. Basically what we wanted to do was classify the connectors, and there were connectors here and there. We didn't know if those connectors were able to the form, or they were brittle or not. So there was significant classification of those connectors with testing at Lehigh University. And once we got to know them all together, we use, hey, those are the good ones we want to use for a test here that is going to be subjected to the shaking intensities that we see at Berkeley or in Seattle or something. So there was the reasoning for the use of the Atlas laboratory, as well as the UC then this shaking table, right? And that's how we divided our work. At the system level, we basically did some analytical work with the testing of at the system level, at the diaphragm level, and also at the complete detailed finite element level was University of Arizona, and leading the team. And the detailed level of the connector properties and classification was all done at Lehigh University with hybrid testing. This is the test itself. One of the things is that the shaking table, it's very difficult to see those who were on today because the building is spilling over the shaking table. But this one did too. You can see this is what we have, the shaking table here, and the building was going all the way there, right? So the shape of the platen itself is rectangular, but it's in the wrong direction for a diaphragm test. And remember, it's only running, the shaking table is running in one degree of freedom, is single axis is going this way. So that way we had to spin over. And that implied that we had to design these outrigger beams and place them in hydrostatic bearings that we actually made them one because it was pretty cheap to economical. Let's not call it cheap because they work very well. Economical work for us. This is one of the tests that we go here. And you can see a low damage wood here. Opening, there is no formation of a plastic hinge. And significant rotations occurring there with barely any damage, and the wood goes back to recently positions. Just going to go fast. This work done by the University of Arizona, able to the post-diction is not a prediction because we have prediction tools and then we have post-diction tools, which are recalibration after the fact. And those post-diction tools actually work very well by the team of the University of Arizona. That enables us to propagate and now design buildings, precast buildings, and put several connections, and we wrote essentially 1,000 pages of recommendations for the precast industry, and that ended up winning the 2016 ASC Pancao for innovation. Let me go to the second one. I will probably be brief there. Is the IFAS project, which is once we look into what we did for the precast concrete industry, we went back to the precast concrete industry and say, let's do some interesting things. Let's look those walls that are low damage, that are post-tensive with energy dissipators, let's put them here. But we now want to decouple, find a way to uncouple or decouple the lateral system from the gravity system. And that requires some use of some kind of connecting elements that can be deformable and dissipated. So we go into the details. That's really Professor Champer's work. Again, this is a project that involved many people, the students, industry, design engineers, universities from abroad, and even middle school in Arizona. Students are the gold mine for these projects. If you have good students, the project runs very well. So, I guess many of you will have top class students that when they come here, they love to work every day on these projects. Unique in many facets and stuff. So the concept itself is that in a conventional system, you have the mass, this is the gravity, let's say this is a blank view, this is the slab itself, and this is the lateral force resisting system. They will go and move together, yeah? But if we want to decouple them, yeah, they will move together like that, taking inertial forces. But if we want to put something like a fuse, kind of fuse that at some point it basically separates and dissipates energy, so we can have something different, right, like that. By doing that, we can optimize, we can reduce the accelerations on the floor and the demands on the walls. And the trade-off is that the displacements on the gravity system may be significantly larger. So we just need to find those domains or feasibility domains where the system can be optimal. Yeah, let me go to 3 slices on media there. So these are renderings of these kind of buildings. They can use BRBs in the connection between the walls, the lateral system, and the gravity system. You can place BRBs or friction devices. And let me show you, as you torture those days. As you do testing at Lehigh University at the component level. These are rubber bearings to provide the restoring so they don't get stuck. If you're using a friction damper, it gets stuck and gives you a residual deformation, but a little rubber bearing is able to push it back and recenter. This is a plug U. Friction damper from the top. And let me go to the next one. This is the bumper. You will be wondering what happens if the deformation exceeds and you hit the gravity system. So the University of Arizona came with this great idea to use like a fender, a bumper itself that can be hit. So this is hitting there. Yeah, takes a little bit of energy away and it goes back. So we had this and we had testing where we deliberately exceeded when we exercise that bumper and saw what happens in the testing itself. Let me go faster. Just one, I talk about the feasibility domain, but I will go faster here to show you some of the testing that we did at UC San Diego. It was a 4-story reinforced concrete building with low damage walls. It was very interesting because in this building, we had, remember, the shaking table was running in single axis, and we wanted to test BRPs, and we wanted to test friction devices as well. So what we say, let's test them in the same test. But how can we do that? I say, well, we put significant eccentricity. We just place one wall in significantly eccentric from the center of mass, and 2 walls here. So this building is going to go that way, and by going that way, we're going to test 1 in the north-south direction, and 2 in the north-south direction, and 1 in the east-west direction. So even with a single axis, we were able to test 2 different systems simultaneously. I'm going to go fast and show you some videos at the end. This is videos of the friction device. You can see the bumper here being hit. And the building itself. You will see, you will conclude yourself that by decoupling this, the video itself talks. The building gets way less excited if you have these devices that uncouple the gravity and the lateral system than if you leave them together. So these are the low damage walls. You see them crack here. You see them crack the up is because they were subjected to torsion as well. But they are going to uplift. You see in the first one, phase 1, where we have the uncoupling, it barely rocks. The phase 2, when the system is working like a monolithic, you have significant rotation and uplift of the walls themselves. And just going to see, let me show this video as we finish here. In one direction and different devices in the other direction as well. I don't have the time. I just want to acknowledge always Professor Robert Fleischman. He spearheaded these 2 projects with tremendous leadership. And I hope that you guys are inspired and can write your own proposals, think with the industry you best like, and begin to get yourself in this wagon. We are here to help. I want to make it very clear that we receive summer salaries from the National Science Foundation. We don't have to be a copy on your project. I'm happy if I'm on an area specialization where I have a technical interest in the topic, I'll be happy to do that. Other than that, we are here to support your testing, right? To support your ideas under confidentiality. You work in a deeper still, so there are people that are going to help you how to design a safe structure. What experience do I have? We are here to help you in your proposal. That's the main goal and the main message that I want to give. Thank you very much.
Alright, so hopefully everybody's having a good day so far. I'd like to give a similar presentation as Professor Restrepo, but focus on geotechnical engineering. I kind of have some unique slides in here because I want to try to convince you of the role of using large-scale shake table testing for geotechnical problems. We do have a choice of where we can test. Like I say on the airplane, you know you have a choice of where you can fly. In geotechnical engineering, we can use centrifuge physical modeling. We can use full-scale testing in the field. We can instrument real systems that are being built, and we can do things on the large shake table. There's pros and cons for each of them, so there's nothing wrong or right about them all. And I think that hopefully I can convince you in this presentation that they complement each other. So first, I'm going to give you a little bit of my thoughts on the role of large-scale shake table testing in geotechnical engineering with quick engineering. First, talking about motivation, and then the need for scaling. So scaling is one of the major issues that we have to deal with in soils because you're never going to be able to simulate the behavior of from the ground surface all the way down to rock, unless you're in some sort of an area that has a very short soil deposit. So we always need to have some sort of consideration of scaling. Then I want to go over some details of the capabilities that we have here in geotechnical testing. You saw the soil boxes today. I'm going to show you some different pictures, configured, things like that. Soil management is a very important issue. This has come up in previous projects at the site. And I think if we want to have geotechnical tests, we need to have a good way to manage the soils. So I'm going to show you some of my ideas. That's maybe not going to be the final things, but with that. And then some other resources we have here at UC San Diego for geotechnical testing. It may be possible to use some of our other equipment on campus on the shake table. Then I'll go over a few of the past projects. You've seen some of them already in Professor Conte's presentation, and then close out with some my thoughts on open issues and future research challenges in geotechnical evaluation. And this is definitely not all-inclusive. There's many other areas that can be explored in the shake table. So it's just a few thoughts to get the discussion going. We'll have a conversation this afternoon, where we can have an open Q&A, and also tomorrow morning. So why do we want to use large-scale shake table tests? In combination with large soil boxes that we can use to confine our soils. And we hopefully can use reasonably sized foundation and structural models to test these systems. So these can complement centrifuge tests. So for those of you who are not familiar with geotechnical centrifuge testing, we're going to test small scale models and small soil layers in the centrifuge that is spinning in a vertical acceleration field that is greater than Earth's gravity. So ng times greater than Earth's gravity. And when you do that, you can have similitude between the stresses in your small scale model and in the field. Because with soils, their behavior depends on their stress need. We can also use these to validate computational models. One of the best things with large scale shaking table tests is that you can use real construction techniques that we're going to be using on real projects. And most of the time, structural elements, either reinforcements or facing elements that are the same as those that you're using in the field. And I've done a lot of centrifuge testing, and we always find ways to make little tiny foundations or little tiny ground improvement elements. They're not going to match the way that things are in the field. And many times you have to wish things into place in the centrifuge. So in the large-scale shake table test, you can install them using the techniques that we install in field tests. So the large-scale shake table tests are best when you can look at full-scale systems. So those are mostly ideal for near surface embedded structures, energy vaults, pipelines, shallow tunnels, and then things like bridge abutments, retaining walls, levees, embankments. All of those things are under relatively low stress states. The heights can usually be accommodated within our containers. You need to choose the right motion so that if you're building a retaining wall on top of the ground, you're inputting a rock motion, that would be like a retaining wall on top of rock. Or you can input the motion at the base that represents the application or de-application of the motion from the rock to the ground surface. It's also very good to study phenomena that can't be studied at the laboratory scale or the centrifuge scale. So we deal with many large particle-sized geomaterials like gravel, tire-derived aggregate. Those things, if you have a very big specimen, you could potentially even do an element scale test on the centrifuge. And we can also look at things like biomediated soils, liquefaction, induced lateral spread, etc. And as we're going to see near the end, we can look at soil structure interaction problems, really accounting for the seismic deformations of either the saturated soil or unsaturated soils. Unsaturated seismic compression is one of my interests at the moment, and I think there's a lot of challenges there to solve. And then also underground pipelines, utilities, connections to structures. Those are all tricky things that need to be studied. Now that we have the 6th degree of freedom motion, we can apply that for soils as well. So when we apply these realistic 3D motions, we know that the properties, the stiffness and shear strength of the soil depend on the self-weight and stress state. So vertical accelerations are going to lead to changes in the vertical stress state. So that's going to lead to changes in your deformation response during earthquakes. In some locations, the vertical component of the motion may be greater than the horizontal when you're at short periods. And there have been several studies that have found that when you have combined either 2D shaking or combined vertical horizontal shaking, you end up having greater deformations than just one-dimensional motions. So in the centrifuge, the nice thing there is that Scott told an example today where somebody built a very, very elaborate model and could only test it one time. But at the same time, it's a very small system, so if you're designing it very simply, you could potentially do multiple tests and do parametric experimental studies. Here, when you're building something on the big shake table, it's going to take a long time, so you don't really have the luxury of taking it apart and putting it back. So the centrifuge is nice in that fact that you could do multiple tests and study different geometric configurations. Centrifuge testing, there's also a lot of cool techniques that can be used. transparent soils, transparent soil boxes, so you can visualize through and see deformation mechanisms, see the movement of various structures. Without having to use any sensors, you can just directly visualize it. That's a little bit harder to do in the large containers that we have, although perhaps they could be adapted in the future. But the good thing about using the large soil boxes on LH Post 6 is that we can use the actual construction procedures, consider foundation installation effects, actual ground improvement, and actual geosynthetic reinforcements. I did one study when I was at the University of Colorado on reinforced soil walls, and we had to go scour the internet to find something that was at a scale stiffness of a certain geosynthetic. We ended up having to go to the material that they put inside of clothes when they're trying to size a suit. It's a very weak material. So with the large system, you can actually use the real geosynthetics. We can also put in large instrumentation. Sometimes when you look at the earth pressure cells, they're the size of the container that you would be using in the centrifuge. You can put in dielectric sensors that need to have some space around them to measure water content in soils, and multiple settlement plates to look at deformations at different depths. You could, depending on the size of the problem you're looking at, minimize your near field and boundary effects, especially when you're doing things like the in situ shear wave velocity topography. So if you have arrays of bender elements, you can send signals to each other, and the boundaries are not going to have this big effect to see how the soil is evolving behavior over multiple shakes. So based on that discussion there, I think there's a lot of opportunities for collaboration between the different the sites. So we definitely recommend those sorts of proposals that potentially use both of those. Maybe you start in one phase doing some tests on the centrifuge, and then you build it in reality on using real techniques on the large shake table. This other point down here, using modeling of models, this is a very important thing. A lot of scaling relationships that we use in the centrifuge need to be validated. And the large scale testing at 1G is one of those models that can be used for validation. And yeah, I mentioned doing parametric studies in the centrifuge. So scaling is very important. Soil dynamic properties are controlled by the stress state dependent effective stress, or they're stress dependent, which is the effective stress. At the prototype structure, I just drew 3 different systems here, your prototype in the field. Maybe you can't build the full scale prototype in the large shake table, so we need to do something maybe that's half scale. But then you can also spin something in the centrifuge at 20 Gs and have a much shorter height. The effective stress in the centrifuge model is going to be the same as the effective stress in your prototype earthen structure, just assuming we're dealing with sand without any water. In the model earthen structure, the effective stress is going to be half that is in the prototype. So it's going to, the stiffness is going to be a lot lower in the model compared to the prototype. In the centrifuge, it's very nice because everything follows very logically and simply, I think, in developing scaling relationships. Our goal is to have stresses be the same in the model and the prototype. So we scale the length by a factor of n, and we use the same materials, so the unit weights are the same, the densities are the same. And when we spin it in the centrifuge at an increased gravity level, then that's the way that your small model has the same stress state as in the. And if you start with this geometric similitude, scaling your lengths, you can end up with several different scaling factors here. I think this is very clean and logical on how these are developed. You get into some more complex things when you look at time effects, but in general, it's easier to deal with this. That's another issue on the centrifuge when you're looking at dynamic behavior. Sometimes you need to use alternative pore fluids. So methylose that diffuses in a slower rate. So when you have pore pressure buildup, if you use water, it would drain too fast from a scaling perspective. So you need to use a more viscous pore fluid in the centrifuge. In the 1G shake table tests, we can use water. So when we try to do scaling for 1G shake table tests, your model is going to be softer and weaker. So your model behavior is going to be like this, and the prototype is going to be like this, and your hysteresis loops are also going to have different shapes. So it's going to definitely lead to different deformation responses. So the earliest scaling factors were developed by this guy Roshop here, and they were extended in 1989 in Japan by AI. And they came up with some similitude relationships that considered geometry scaling, the same as the centrifuge, but then also scaled the density and scaled the strain. So it's much more complex when you're suddenly scaling 3 different parameters as opposed to 1 parameter in the centrifuge. And he looked at the equilibrium and mass balance and came up with several scaling factors that I'll show on the next slide. This is really only applicable to smaller strain behaviors. So here are the scaling factors that can be used. The ones that I'm showing here, we have a scale factor for length, density, and strain. So these are 3 separate values. And then these are all of the different values. So your stress is on the scale of lambda times lambda rho. Your stiffness is very complex scaling. It's not as easy as doing it in the centrifuge, but if you perhaps choose the right conditions, you can come to the case where your density and strain scaling factors are close to 1, that you can assume that they're 1, in which case you can simplify the case and drop off all of the other terms. So if these are 1, then these are the scale factors that you would use for G scaling. So the goal, we're going to change our soil conditions so that the normalized stress strain plot between the model and the prototype are going to be the same. So these are the model and prototype, and when we look at them on a normalized basis, they would have the same response. And normalized by the confining stress, shear stress divided by confining stress. So this is just an example of what would happen if you use the same density of soil at 2 different mean effective stresses. So because the prototype is under a higher confining stress, it's going to be stronger and it's going to be stiffer than the model. When you normalize this, the deviatoric stress or shear stress divided by the confining stress is going to be a big number divided by a small number, so it's going to be higher than the prototype. So you can see if you use the same relative densities, you don't have swing. So we had a study where we were trying to do some half-scale retaining wall tests, and we kind of had to do several tests at different relative densities and try to find the one where the normalized behavior was the same between the 2 between model and prototype. So we found if we reduced the relative density down to 70%, then when we tested it under the lower confining stress, it had a similar shape and also a similar peak. I didn't mention here that because these are having the peaks happening at the same value, you can assume that the strain factor is 1. Another challenge, and then the other nice thing is that your secant modulus, the scale value, is very similar between the model and the prototype, which is good. But then you're saying, well, you've now just used a smaller relative density than in the prototype, so you can't use the same density scaling factor of 1. But relative density is normalizing things between the maximum and minimum relative densities, so the difference in actual unit weight or density is not very high. So if we go from 85 to 70, you're going between 119 and 115. So it's not that big of a difference. So we assume the density scaling factors. So there's a lot of additional rigmarole that you need to go through to use these scaling factors from the ICE approach. If you're trying to do reduced 1G testing, but it's possible. One possible research avenue would be validating these relationships using centrifuge models. So our facilities here, I need to go quickly because I spent too much time on that. We have the laminar soil box. This is what it looks like when it's all assembled. It can have a height of 4.7 meters, so 15.2 feet, so it's pretty tall. I think that Ahmed has also extended the height of this a little bit from the time that this was last used. This was from Nice. We have the rigid soil box. This has been used for 3 tests, and I'll talk about those later. This is good for simulating plane strain problems, where we have a long strip system. We have a wide range of sensors. The nice thing, when you're using centrifuge tests, all of the sensors have to be very, very tiny, and placing them can be very challenging. Here, there's a lot more options on what we can use between string pods, potentiometers, accelerometers. And because you don't have to scale the acceleration like you do in the centrifuge, you don't need to have this fast of response as you do in the centrifuge. You also put in settlement plates, earth pressure cells, tiltmeters. Soil management is a challenge. If any of you had visited 4 years ago, there was a huge sand dune right here, 2 different sands. Unfortunately, those are now mostly, I was joking when we were there, used as backfill on some different projects here on campus. Some of it is being stored over here, and some other soil is being stored over here. But I think in the long term, if we want to use this as a geotechnical facility, we need to have an approach on how to manage the soil. I found some pretty interesting containers that they use in agriculture, bottom hopper type containers that you can fill this with soil, pick it up with a forklift. It has a hole in the bottom that can be opened and closed. And you can stack these out of the way. There's probably going to be some UV degradation, but not as bad as the super sacks that we use at the moment. And once you use this, you could actually lift it up with a crane and bottom dump it into the containers. We do have a conveyor belt that we use to load that system. The other good thing about our site is we have a lot of different earthwork materials: a bobcat, front-end loader, forklift, and crane. Those are all part of the site, but they're available for recharge. I also have bought a vibrator plate compactor and whacker packer that can be used. We have the soil pits that you've seen there. Here's a picture of the soil pit was excavated at one point. We have the policy that new users should budget to remove the previous test before doing a new test. That's kind of the future going forward, because we have a test that has been there for 50 years or so. But it's a very nice facility because it has a very large reaction mass actuators that can be used to load foundations vertically or horizontally and potentially vertically. We also have a lot of large-scale testing. It's available on campus. And we have other containers, smaller ones. So maybe you don't want to go to the huge laminar container. We have a smaller laminar container that's still pretty big. It's 11 feet or so high. I just finished using that. I'll show some pictures. We have a small rigid box that can be used as well. It has a transparent base. We have a centrifuge here that is available on recharge through the Powell laboratory. It's not as big as the Davis centrifuge. It's not as small as the Shavitz size centrifuge. We just finished using it to do some rocking foundation tests with Professor Hutchinson. Past projects, I'll go quickly through these. I think one of the first geotech projects was this lava earth pressures on a rigid retaining wall. And here they compacted the soil using real techniques. They can use density gauges to see the reactions. They were able to get the earth pressures as well from hydraulic jacks to keep the wall in position. In the large rigid container, the full-scale geosynthetic reinforced wall, we're still waiting on the publications out of this test. One of our laboratory technicians, previous laboratory technicians, did his PhD in this talk. But this is one of the cases where they assembled the box. It cost maybe $40,000, we're estimating, to build the box on the table. But once you built it, Professor Cutter came along and did some rocking foundation tests with heavily loaded foundations. It was unidirectional at the time, but now we have the capabilities to do multi-directional testing. And that's especially, we can do that in this container because it's rigid, it can move in multiple directions. The laminar container is still just one directional. And then after that, there was a test by Don Cheng from UC Davis, where they put soil here and then put a cantilever type retaining wall, and then put tire-derived aggregate on top of this, and then layer of soil. And the interesting thing that they found here was that the tire-derived aggregate has a unit weight about half or a third that of soil. So the downward force on the toe, the stem of the retaining wall was low enough that they had a huge amount of sliding. So it was an interesting feature that they observed. You saw the pictures of lateral spread in Al's presentation this morning. Here's another very creative set of tests that Professor Elganal did. He first started doing some tests for Caltrans on a cut and cover type tunnel, where they were looking at the racking response in the tunnel. And after they finished those tests, they took the top off and then simulated the behavior of the dam spillway. So I thought that was creative reuse of almost the same structure, but with a different configuration. And that was for the river reclamation. And then on that same test, Amy Serrato did a payload project and installed several helical anchors and loaded them with different masses and looked at their dynamic response. And this was the first set of dynamic tests that had been performed in this one. So some quick thoughts on future tests. Soil structure interaction testing. Professor Conte mentioned this before. You can do the tests with no soil, which is not really a geotechnical testing. I think that this middle set of tests where we put the laminar container or the rigid soil box there, fill it with soil, have your foundation there, and do the shapes and study soil structure interaction. That's the best because then we can see the effect of the nonlinear soil response on the soil structure interaction. Other interesting things, gravel liquefaction. I borrowed these slides from Ada Avalos Zekos from Berkeley. So one challenge that she has is to study the cyclic response of the large gravel. She has to have a very large cyclic simple shear test. There have been cases where gravel liquefaction has occurred, and there is a need to update these triggering diagrams for gravel and different mixtures of gravel as well. Rocking foundations with ground improvement. There's been a lot of study on rocking foundations in general, but there's a peer project that I'm working on with Professor Hutchinson where we're trying to use ground improvement to strategically improve the soil so that we get better rocking response. Here's just a rocking response of non-reinforced soil layer and a soil layer with ground with dust. Cement columns, which are kind of just little tubes of plaster of Paris, and there are different scales, but there's a much smaller settlement and a little bit better recentering with the ground. We've also used geosynthetics on this, and it works well. We did this on the centrifuge, so it's all very small scale, so it would be nice to do this on a larger scale. We just finished these tests this quarter on using tire-derived aggregate as material to place beneath foundations as a low-cost seismic isolation. I don't have a video in this presentation, but I have it on my phone in case you want to see it. One issue is that there's a lot of settlement, but it has very good recentering and very good energy dissipation. We've also done tests on the Powell laboratory shake table, which we still want to do on the large shake table on GRS IBS walls. FHWA is pushing very strongly for use of these GRS IBS walls in practice. I think that this would be the case of advanced bridge research that would fit into the ECI area. But Caltrans doesn't like the idea of putting a bridge deck directly in the soil, so they wanted very complex footing within a reinforced cement piece with a bridge deck on top of it. We studied this in some tests here, but I think in the future I want to study these GRS ideas on the large shake table. And then MSTDA walls. Instead of putting the TDA on a cantilever type retaining wall, why don't we use a geosynthetic reinforced retaining wall, but with the TDA? We've done a lot of research on the material properties of these, and it has a very high damping ratio, but relatively high shear strength. So it's a lightweight alternative. You can look at rail embankments as well. Seismic compression. This has been identified as a major cost in the Northridge earthquake by Jonathan Stewart at UCLA. And yeah, just to wrap things up, I think it's an appropriate facility for a range of geotechnical and soil structure interaction problems. It fits into the suite of tests that we have. We can test these phenomena that can't be studied on other scales. Soil structure interaction is a great approach for the shake table because we can look at the effect of these seismic deformations and nonlinear behavior in the soil. And yeah, so with that, I think I'll end so that we have time for our next speaker. So thank you. Giving our keynote presentation this afternoon, Professor Scott Brandenburg from UCLA is here to talk about his experience with soil structure interaction. Very happy that you came down today, Scott.
Yeah, the traffic was really easy. Hopefully it'll be easy going back. On cyclic failure of fine-grained soils. A lot of this will be related to centrifuge modeling. That's primarily what I've done. Although the seismic earth pressure, I use other people's data. So that's a great thing too. You can go look online and find a whole bunch of curated data before you do an experiment or propose one. It would be good to do that just so you know what's out there. There's a whole bunch of good data out there just waiting for people to use. So first, what is soil structure interaction? Well, it's a coupling of the structural and the soil responses. And the coupling means that you really can't just isolate one and then do the other one, right? The structural and geotechnical engineers really kind of need to work together to solve these problems. It can be modeled using a lot of techniques. A simple one is just to put springs on the bottom of a structure instead of modeling it as a fixed base. That's a substructure method, so it's very common that geotechnical engineers will provide structural engineers spring constants to put on the bottom of a model and perform SAP or something like that. Or you could go fully nonlinear with continuum elements for the soil and then structural elements. They could be continuum or beam column or plate or something like that. And that's another way of dealing with it that's more kind of fundamental, computationally complicated. But SSI is really commonly ignored. So I'll talk about two problems where SSI is usually ignored and it's resulted in problems. So why is it often ignored? Well, one is that it's just easier to not deal with it, right? I'm a geotechnical engineer, I just want to do my soil stuff, and you structural engineers can do your stuff, and we don't have to talk. So I think a big part of it is that SSI requires communication between structural and geotechnical engineers, and we like to kind of stay inside of our own little area and not deviate too far outside. But as with a lot of multidisciplinary research, I think there's a lot to learn right at that interface. So it may be important to kind of form collaborations with other people to do this sort of research and feel comfortable kind of stepping outside of that comfort zone. So here I think she's the geotechnical engineer explaining, like, you can't just model it as a spring, right? What is one spring going to do at the bottom of the structure? All right, so I already went through this. I'll talk about two projects, do a real quick run through. If you have questions about them, feel free to ask me, after the presentation. So seismic earth pressures on flexible vertical retaining walls. Seismic earth pressures is an area where geotechnical engineers really drive structural engineers crazy. We often give these earth pressures that are so big based on the existing methods and that we use to compute earth pressures that it's really not feasible to build them. Basement walls for structures become a meter thick sometimes, reinforced concrete, and there's no reason for that. Basement walls that were never designed for seismic provisions perform well during earthquakes for the most part. It's pretty unusual to go and see problems with retaining walls after an earthquake. It has happened, it's just not that common. And then I'll talk about this ground failure potential. So these are all the people I've collaborated with on these projects. Jonathan Stewart's involved in both of them. He's played a key role in kind of transitioning the seismic earth pressure part into the NHERI provisions. Jason Binker did centrifuge modeling at UC Davis. So if you're proposing to do projects remote, it would be, you know, at another facility, it's good to talk to people who have done that. So he had to go live at Davis and was married. His wife wasn't happy that he was leaving all the time to go live at Davis for weeks on end. So these are all the logistical details that become really hard about doing projects remotely, but he had a great experience, right? So it can be a really good thing for the students there too. Maria Giovanna Durante was a visiting scholar at UCLA and then a postdoc at University of Texas before moving on to the University of Calabria. And she did a lot of the numerical modeling, the seismic earth pressure part. And then George Milanakis there at Khalifa University, he requires us to solve everything analytically using equations, no numerical things at all. If the solution fits on like an 8.5 by 11 piece of paper that you don't have to rotate sideways, then it's not good enough, right? You gotta do it better. All right, so seismic earth pressures first. The most common way we deal with seismic earth pressures is to use the Mononobe-Okabe method. Mononobe Okabe is not a Star Wars character or something like that. These are researchers who did some really pioneering great work in Japan quite a while ago now. Okabe came up with the original theory back in 1924, and then Mononobe and Matsuo did some experiments that kind of validated that theory or compared it with the theory in 1929. You don't see Matsuo in there. I don't know what happened to Matsuo, right? It should be Mononobe and Matsuo Okabe, but that's just a lot to say. So basically, this is a limit pressure method. We assume that the soil is failing, right? So during shaking, the soil is going to fail, and it's going to push on the wall, and we need to design the wall to hold all that pressure back. So we start with the static one, and then we compute, based on limit equilibrium, how much pressure is there from shaking. And we represent that with the seismic coefficient, KH, which is basically like a horizontal acceleration in G, you can think of it that way. And then we have this failure wedge, and the failure wedge is accelerating, and we alter the angle of that failure wedge until it is maximized in this case, and that gives us the PE, which is the seismic pressure, and then we often will take the difference, and that's the seismic increment. We assume it acts at some height above the base of the wall, and we can design the wall for the resulting bending moments at the base. This equation for KE up at the top is basically how we compute PE, right, the seismic increment. It has some problems. If you put in certain combinations of input parameters, usually involving very high shaking levels, like higher than half a G or 0.6 G or something like that, you either get infinity or an imaginary number, right? So obviously there's something wrong with this equation. Usually you'll get the imaginary number first before you get infinity, but it won't produce a physically meaningful solution a lot of the time for design level ground motions. So some of the things that people have done is to say, oh, well, let's take the shaking intensity and divide it by 3 and then put it into this equation and then multiply it by 3. That would work fine if this was a linear equation, but it's not, right? So you're kind of not really adhering to the fundamentals of the theory anymore when you take shortcuts like that. And this is why we make the structural engineers mad, right? We're saying, oh, the earth pressure is infinity. Go ahead and design your structure to deal with infinity, right? And then I mentioned earlier the empirical evidence is that retaining walls perform well. Even if they're not designed for seismic loading and maybe really old, built a long time ago before we even had seismic provisions, they're fine. They just move along with the soil, and obviously these earth pressures that we're predicting are not true in all cases, even though they were in those experiments by Mononobe and Matsuo. So a couple of questions for you. First, does horizontal acceleration necessarily give rise to lateral earth pressure? There's an assumption here that it does, right? If we have horizontal shaking, there must be earth pressure that comes out of that horizontal shaking. That's actually not true. And the second one, is seismic earth pressure influenced by factors that are not considered in the Mononobe-Okabe method? Like the flexibility of the wall, right? If you have a flexible system, it may not attract much load from the soil compared with a very stiff or rigid structural system. So this is where the SSI comes in. So our procedure that we've developed uses soil structure interaction principles. So first, let's talk about this relationship between horizontal pressures and surface acceleration. I didn't animate these on purpose because I get tired pushing the buttons. But if you have a acceleration time series at the surface, let's just say that it's harmonic. Our solution is done in the frequency domain, so we analyze each frequency component by itself, assuming linear elasticity. If there is some shaking at that frequency, you can represent the standing wave as a cosine function with zero strain right at the surface. And if the soil is linear elastic, there's actually no change in horizontal pressure from vertically propagating shear wave. Right? All of the stresses are taken by shear stresses that are on horizontal and vertical planes. There's no change in vertical pressure, there's no change in horizontal pressure. So you definitely can get shaking at the surface without having a change in horizontal pressure. And if you were to make an excavation and replace it with a magical retaining wall system that had the exact same mass and stiffness as the soil that it replaced, that structure would also have no seismic earth pressure. Right? So that may be why some of these retaining walls that were never designed for seismic earth pressure actually perform pretty well during earthquakes. All right, so I did animate one thing. I think that equation just turned gray. Pretty fancy. I'm from Hollywood, right? So that's a special effect right there. All right, so our approach is a little bit different than the traditional approach. It's not limit pressures anymore. What we do is we assume that we can represent the wall as being a beam, or a plate in this case, with some kind of flexural stiffness. It's resting on a footing. Maybe the footing itself is also flexible, so you could have some rotation and translational stiffness. And then the interaction between that beam and the soil is represented by what we're representing here is springs. It's actually a continuous stiffness intensity, and we integrate analytically because George made us solve equations, right? So springs would be a numerical representation. We're using a continuous stiffness intensity represented by this case of y with a superscript I for intensity. And then one thing is that the Mononobe-Okabe solution does not consider the frequency content of the ground motion. But if we think about it, frequency content of ground motion should matter. I'm going to try and get the laser pointer here. All right, got it. So low frequency waves have a long wavelength, right? Or if the soil is stiff, the wavelength is going to be pretty long. If you have a fairly short wall, it just kind of moves with the soil back and forth. There's no relative displacement between the wall and the soil. That's what really causes earth pressures to develop. On the other hand, if you have a short wavelength like this, then you get big earth pressures because the wall can't conform with that soil, especially if the wall is fairly stiff. If the wall is flexible, it can move with the soil a little easier. You might get less loading on the wall. So when Mononobe and Matsuo did their shake table test, it had a rigid base, and there was the wall, and they shook the base and got a short wavelength because that soil layer tends to amplify a certain frequency, and that frequency will cause big strains in the soil, and you get big earth pressures. If they modeled it as being much deeper, they probably would have seen something much different, right? Lower earth pressures. So they did validate the theory, but under a very specific set of boundary conditions. So what we did was looked at, instead of acceleration, kind of as our predictive variable on the x-axis, we put wavelength divided by wall height, right? So this is kind of a fundamental SSI parameter. If the wavelength is really long compared to the wall height, you get very little seismic earth pressure out here. The y-axis is kind of a dimensionless earth pressure resultant. If that becomes short, you can get pretty big earth pressures acting on the wall, actually bigger than Mononobe-Okabe sometimes, right? And then another thing that happens is that there's flexibility. So we represent flexibility by beta h. If this beta h number is big, it's very flexible. If it's 0, it's rigid. And so this comes out of the Winkler solution to the governing differential equation that we're solving. I won't go through what all of these, how we derive that or anything. It's a fourth order ODE, pretty non-homogeneous. It's not that hard to solve it. But you see that the wall flexibility drives the pressures down a lot, right? So the lines get lower and lower. And maybe more importantly, the resultant height gets lower and lower too. So if you have a pretty rigid wall, the line of action of the seismic increment is up there around 0.6 times the height. That'll produce a lot of moment about the base. If the wall gets more flexible, it puts the resultant lower. So you reduce the pressure and you reduce the height of the resultant. So the bending moment at the bottom goes down too. So you may be wondering, well, this is great. How do we get wavelength over height? I know how to get PGA, I can go to a USGS map and look that up, or do a seismic hazard analysis or something like that. Well, what we do is use peak velocity. So there are ground motion models for PGV, right? PGV is fundamentally related to strain. It's not such a high frequency parameter like PGA. We have a little correction that we apply to it, and then there is an angular frequency or a mean frequency of the ground motion here. And to get that, we use a procedure that was developed by Professor Rabji, who presented earlier, right? So quite a while ago now. This may need to be updated sometime soon, right? 2004 seemed recent at the time that I read the paper, but it's no longer all that recent. So anyway, you can get, just like for PGA or PGV or spectral acceleration, they're ground motion models for mean frequency of a ground motion. So you can come in and do that too. It depends on magnitude and rupture distance and things like that. Then we just have some fairly simple correction factors that we plotted out in this. This is the Part 3 resource paper in the NHERI provisions. So a Part 3 paper is basically like, we think this is a cool idea for people to consider as part of building code changes. So it's kind of like the beginning of ultimately getting something in ASCP 7 or the final NHERI provisions get adopted eventually part of the code. And these are, just some plots that are usable at a design level, just easy calculations to do in a design office. All right, so we developed this theory. There's actually multiple iterations of it. This is a very simple one. Some of them are like frequency domain solutions with complex stiffness, and there's a whole range. The simple one is actually pretty accurate, but you can get better solutions if you're willing to invest a little bit of extra calculation. But we needed to validate it, right? And so instead of proposing to do some model testing, we went to DesignSafe to see what's out there. People have done experiments on this already, so we might as well use data that's already existing. So here's one that was published by Professor Sitar's research group, right? Seismic earth pressures on retaining structures. They did a bunch of centrifuge tests and made the data available, which is really wonderful because now more people can benefit from it. And you can see we may want to come in and interpret the data differently than they did, right? So sharing data enables that because we can come in and get the data and now do calculations on it that are different from what the original authors did. That's why I really like sharing my data. I like it when people come in and interpret it in new ways that are creative and interesting as part of the learning. So anyway, if we kind of plot those tests by Sitar's group, or the bottom 3 right here, then we've got some other ones from Shadid Dashti's research group at University of Colorado, also centrifuge tests up here. And this is a numerical modeling study by Farhan Ostadan using a program called SASE. If we plot those in the traditional way, this is kind of like earth pressure versus PGA, you can see that the data are kind of scattered all over the place, right? Here's the Mononobe-Okabe curve. You can see how it curves up really high. You get these very high earth pressure coefficients. This is one by Seed and Whitman that linearizes that. But anyway, sometimes they're quite a bit below. Like over here, the Mononobe-Okabe prediction would be many times higher than the measurements. Actually, you'd probably predict an imaginary number for this one. But then if you look at the numerical modeling study, the data points are actually higher. So this is higher than Mononobe-Okabe for fairly low shaping intensities. So PGA is just not a great predictor of this, right? All of those other things matter: wavelength, structural stiffness, and things like that. So if we look at our method and compare it with the data, it's not like we have a bunch of points exactly on the line that we're predicting. That would be, if you ever see a geotechnical engineering paper that has that, they've cheated. There's something wrong. That doesn't happen. But the trends are definitely more reasonable, right? The data points are following the trends that we're predicting from our model. So structural stiffness represented by the beta H and the lambda over H, all of that matters, and it's showing up in the predictions here. And I have that slide twice for some reason. So one less slide than we thought. So I'll move on now to talking about the ground failure project. And I'll try and get through this quick because I think that my time's almost up here. So when we evaluate ground failure due to liquefaction or cyclic softening of fine-grained soil, we usually do that for level ground conditions in the free field far away from any structure. Of course, we want to estimate what's the effect of ground failure on structures, right? If liquefaction happens in the middle of a field like this one in the Imperial Valley, down where I grew up, just about 100 miles east of here, you know, who really cares? The farmer can come plow this field. There was a sand boil, which is great to go take a photo. If you're a geotechnical engineer, you have to go take a photo of a sand boil someday. It's like a rite of passage, right? And when we do have this kind of level ground, it's easy for us to analyze it because we have the shaking at the surface, and then we have shear stresses at depth. We evaluate those shear stresses on horizontal and vertical planes, and that's what we use as an input to our model to compare with laboratory tests or field observations about whether ground failure is going to happen. But I do want to just point out, we can also represent that in a fundamental way using Cauchy stress tensors, right? So you can put the initial tensor here, and what's happening is you're changing the stress, but only one component, right? Because this matrix is always symmetric, so we're only adding shear stress on horizontal and vertical planes, and we get a final tensor like this. If we have a more complicated thing, like a structure on top of the soil, like what's shown here from overturning of this building in Coachella that Professor Gray took the photo of, right? The ground failed beneath this structure. It wouldn't have tipped unless the soil got weaker. But you didn't see free field evidence of any kind of liquefaction. There were no sand boils, no ground failure off in the free field, just beneath the structure. So that's an indication that the structure contributed, right? It's not just free field shaking. The structures can contribute, which seems obvious, but is often ignored. So anyway, if we have a shallow foundation and we can cooperate with our structural engineers to get base shear and moment and things like that to put in, what we can do is estimate a more complicated Cauchy stress tensor that's maybe fully populated, right? So it has stress components in all of the different locations. The only problem is now, what do we do for our cyclic stress ratio? It's been based on horizontal and vertical shear stresses. We can't really use that anymore because there's all these other more complicated stresses happening. So the thing that we did, this is the work that Jason Vinker did on the centrifuge. We used elastic stress solutions, which are given by these equations right here, to estimate the stress tensor at a point, right? So there's the initial stress that changes from the presence of the structure, then there's the change in stress from the shaking as well, and we can get those stress components. And then we've defined a cyclic stress ratio that is based on principal stresses. So not single stress components anymore, but we take the eigenvalues of that Cauchy stress tensor to get the principal stresses, and we can use the deviatoric stress invariance and the mean effective stress. So two things that don't depend on coordinates. You know, you rotate coordinates and those things stay the same, right? They're invariants. And we can come up with this definition of CSR, right? So this is an invariant-based one that should work for any stress path, not just direct simple shear stress path. And use it to predict ground failure beneath structures, including these more complicated stress paths. So we did a set of centrifuge experiments at UC Davis. Our structures were aluminum I-beams with steel masses mounted on top of them. So we have this very complicated soil model, incredibly simple structural model, right? This is like the equivalent of doing a fixed base analysis of a super complicated structure and ignoring the soil, right? We're all guilty of doing these things. We never, we often don't fully work together. But the fact is, on the centrifuge, like John was saying, it's really hard to do good structural modeling. Everything is so small, we can't really model reinforced concrete on the centrifuge. We've spun this model at 60 G, so you have to build something 60 times smaller. There's no way you're going to have the right aggregate. Forget about getting rebar, right? It just doesn't work. So we study like the mechanisms, and so we did these aluminum I-beams. There were two portal frames and one kind of single degree of freedom structure here. And then we had this clay, and we did lab testing on the clay. You can see this is a ratio of the cyclic strength to the monotonic strength as a function of number of loading cycles. So if you apply stress that's equal to 0.8 times the monotonic strength and shake it with I think 13 cycles, that soil would fail, right? Something like that. And these are example results. So we shook it. We're just looking at structure one. We have this for the other structures too. But you can see this is the rotation of that structure. So it did start to rotate. We got 2 degrees of permanent rotation. That's a lot. This structure was visibly tipping, and it eventually did all the way tip over and fail. It's another thing to think about if you're planning a project, right? If you want to induce a failure, make sure it's not going to break stuff on the equipment. We had to be careful not to break LVDTs and other sensors and things like that here. And this is the settlement. So it's settled by almost 10 centimeters in prototype scale. So that's not 10 real centimeters, right? It was a 60th of that, but anyway. And we measured the base shear and moment, so we could get those things directly for this structure. And then we put those into our elastic solution prediction. And maybe just for the sake of time, we can look at this bottom plot down here. This is the factor of safety against failure of that clay soil beneath the structure for this entire motion. So we kind of took the broadband time series and represented it as an equivalent uniform number of cycles, and then we can get a factor of safety at every point beneath the structure. You can see those factors of safety are pretty low beneath the corners of the structure where the loading is high. If you looked out in the free field, they're barely getting below 1. Even if you get a little bit below 1 for a clay like this, it's not going to show up, right? You fail it a little bit, you'd never even know that happened. But if it happens beneath the structure, that structure has adverse impacts, right? It rotates and settles. So here's the result. If you plot this, what we did was took the average factor of safety over a vertical line from the bottom of the footing to the bottom of the clay, and plotted that on the x-axis here versus the dimensionless settlement of the structure. So S is settlement, 2B is the full width of the footing base. In SSI, for some reason, B is half of the footing width. I think it's like a circular foundation symmetry thing. So we always deal with 2B, just like Shakespeare, 2B or not 2B, right? Anyway, this is the settlement divided by the footing width. You can see when our factor of safety drops below 1, we do start seeing settlement of the structure. I don't know if there's really a good predictive relationship between these things, but it is showing that if the factor of safety is higher than 1, you don't get much settlement. When it goes below 1, you do. But if you use a free field factor of safety, which ignores SSI, we're looking at just out away from the structure, what happened? We hardly ever went below 1. And so the structure started seeing pretty big settlement at factors of safety using traditional methods that would be higher than 1. So it might not predict this, right? This would be unconservative, potentially. In other cases, the presence of the structure might actually make it better. If you have a pretty heavy, very flexible structure, like a water tank or something like that, the weight of the structure may make the soil stronger, but then it doesn't shake a whole lot because its period is so long relative to the input shaking. So the SSI can be good, it can be bad, it just depends. So a couple of conclusions, and I'm hopefully getting us a little bit back on time, right? So SSI problems are inherently complicated because they combine structural and geotechnical disciplines. And that's complicated technically, and it's also complicated sort of socially, right? Because we do, even though we're all usually in the same department, we do kind of live in different areas. And we don't always talk to each other. I'm certainly not a structural expert, right? The physical modeling studies really provide key insights into fundamental mechanics that allow us to kind of distill the problem down, right? The thing that I'm interested in is not making a physical model that actually represents perfectly reality. You can't do that in the centrifuge. But you can model a mechanism and then test it against a hypothesis. And then, of course, the field is always much more complicated than our models, right? So you can account for that separately. And hopefully you can distill it into something that's simple and straightforward to implement, right? It's very common that people will say, I did this experiment, I did this super complicated 3D finite element simulation, and look at how well things match up. Well, that's great, but structural engineers, geotechnical engineers are not always going to have the resources to do that level of analysis. So you really should be thinking about how to make things simple enough that people can use it. And a lot of the time you can make it simple without sacrificing a whole lot of accuracy. And that's a good path forward, in my opinion. All right, the third point, publishing experimental data is extremely important, right? So if you do get projects funded through NSF, you're required to publish your data, but you should really want to do it anyway. And the reason is that it will have, your work will have more impact, right? Other people will use it. I think a lot of the time people are worried that if I publish the data, somebody's going to come steal it and publish it before I can publish it. That's a common thing that I've heard people say. I've never seen that happen in real life. And even if somebody did steal your data and publish it very fast, that would be kind of unethical. It's not going to prevent you from publishing anyway, right? People are going to trust the person who did the experiment more than somebody who stole the data anyway. So anyway, I would encourage you to kind of adopt this mindset of really sharing data. It was instrumental in our seismic earth pressure work, right? We use other people's experiments, which is great. So then also, I presented centrifuge modeling studies today. Our structural models were really simple, right? Aluminum I-beams. They stayed elastic. There's no nonlinearity or anything like that. I think there's a huge need to validate some of this on more realistic structural systems, right? SSI, really you should get the soil right and you should get the structure right, because both of those things matter. And that's, I think, part of how the big shake table can fit in, right? You can do experiments with actually like real reinforced concrete, and soil is prepared in a real way. All of our soils are like air fluviated, which is not that bad, but it's not like if you have compacted fill, you can actually compact it the way that it's done in the real world or something like that. So I think there's a lot of potential in this SSI area. So I will acknowledge some support, right? The seismic earth pressure work. Maria Giovanna's time was supported by this Marie Curie grant from Italy. It's a pretty prestigious grant that she received. Otherwise, we didn't do experiments, so we didn't have an NSF project or anything like that to do this work. We used other people's data and just kind of developed the theory for fun over a couple of sabbaticals that George spent at UCLA. And then for the ground failure potential, that was an NSF award. I was the PI of that and ran the experiments up at UC Davis. Happy to talk to you about some of the challenges of managing remote projects. It definitely can be really great, but there are some challenges with having people work remotely too. And then here's some of the references. So I'll go ahead and stop there, since I think I'm already like 7 minutes over. Right? We're good? All right, thank you.
So now in our agenda we have general questions and answer session. So if you have questions for any of the speakers this afternoon, now's a great time to ask questions. But it's also time to share thoughts, a brainstorming session. So if you have an idea and you want some feedback from some of the people that are here today, it's also for that. We'll also have time tomorrow for similar type of question and answer. So if you go home tonight and think about something in the shower, which is usually the best place for thinking for anybody. It's the only place that you can escape from some things in your life. Anyways. So yeah, any questions? Robert, do you have
Yeah, just a quick question about the soil box.
Yeah.
So I guess like, I don't know if you guys have tried you saturated the soil and you noticed any leaking of water, I don't know, like.
So I didn't show a picture. I think there was one incidental photo there, but there's a neoprene sleeve inside of it. It's watertight. And there's a standpipe that takes up one corner of the box. So you can saturate from the bottom of the gravel layer to the base. You can't guarantee that it's fully saturated. That's one of the biggest challenges of saturating the sands. In Buffalo, they do hydraulic fill. So they have saturated sand, and they pump the sand and water together into the tank, so you know that it's saturated.
John, in the Rocking Foundations project, we did saturate the soil, and we actually sampled it several times to check. It had a lot of water, actually.
Yeah. Yeah, on the centrifuge, one of the nice things there, you can actually put a lid on top of it, flood it with CO2, which is heavier than water, and then put a vacuum on the top, and then pull water in. So you can make sure that, you get confidence in your solution.
So this kind of goes back to what Scott was talking about, with like managing things remotely. I don't think it's been touched on for this facility today, but how, these are long time building this. How does it work with like grad students if they're coming from a different school, and same with like faculty in terms of their time being here? How have people, I guess, manage that?
So yeah, I think Ling tomorrow is definitely going to touch on that.
Oh, okay.
He's been here for a while. I think John Vandland is had to go home for a family vacation. Is there anybody else that's managed a long-term? Yeah. Sorry, it's you.
Thanks, Robert. Yeah, so you should plan and budget to be in San Diego, at least during the testing. You end up being, the general contractor. If you're managing this project, you're going to be the person on site, making sure that things are working. And so just budget that into your proposal. And I think I wasn't here for the morning presentation, but you're not going to be able to budget everything on the NSF proposal. You maybe are then leveraging contributions from others, but I'll share some ideas tomorrow as well on that.
Maybe I'll add a few things. I haven't done a remote project here at this facility, but I have done them at Davis. So the amount that you budget for travel, you should probably multiply by 2 or 3 your initial estimate. It always takes longer than you think it's going to, and then the housing costs can be high. I think I budgeted $20,000 a test for travel for the student to go to Davis, and it still wasn't enough. So the other challenge is, students taking classes, are they going to have to be doing the test while they're taking courses at your university? Did they take a course here instead? Or have they already advanced to candidacy? They're done with courses, there are a whole bunch of those kind of logistical issues that come up. But the main recommendation is just budget a lot more than you think you're going to need, I would say. Okay.
Have you been on an NSF panel where the travel budget is a topic of discussion? Or?
No, I mean, I've been on NSF panels. It wasn't an issue when I budgeted $20K per test, right? That was a big part of the budget. And it just seems, I think that if you can say, yeah, I think this is what it's really going to cost, then it's good. You should ask for the money you think you need to get it done. You don't want to be in a position where all of a sudden you're having to cut other things that are important to the project because the travel is so much more than you thought it would be.
Right, I would just add, I think Jose mentioned, he talked in units, and he talked about 1 NSF unit and 3 other units for some of these projects, and that's very realistic. And so even in terms of all other budgeting that you're doing, I like that idea. Whatever that 1 versus 3 is, that's a great suggestion. The other thing, especially on the shake table, recently there was COVID and there was all these other things, right? But things take longer than even if you're talking with contractors and they say, oh, we can do that in 2 weeks, right? Yes, but not necessarily on a research project. And so training contractors, training folks to also understand and budget that correctly as well is important because it's working research and it's not folks at the site are great, so it's not anything related to that. It's just it takes longer, right? And they're very specific things. And so budgeting time as well, and then being flexible. Scott was mentioning, students, are they moving up to candidacy? Maybe students have graduated, and you actually get to do a shake table test, and you have to bring in another student that wasn't the one to bring the design of the project. So trying to be as flexible as possible and understanding that these things may come up, and that's part of the fun of doing the work.
Does anybody have any questions on preparing a proposal for the site, like the different stages?
Yeah, just I don't know how much trouble it was to put in the soil box. It seems like it's a lot of work. So I was just wondering, is it better to have like, because I heard from the speakers, it's probably better to have multiple purchases for the setup, right? So, but what should we do? Like, should we come up with just one idea? Because I would imagine if you just have one objective for your research, and it'll be more challenging, or you would see more obstacles for NSF to agree, okay, let's put on that soil box there, or versus we have a bunch of geotechnical faculties here and propose something that we can share that box. So what is your thoughts on that?
So maybe I can comment on the multiple projects using the project, but maybe Joel. The question was, if somebody wants to use one of the soil boxes, how is the initial cost covered? Can you explain that?
Yeah, sure. So the structure the site is responsible to attach the specimen to the shape table plastic. So for the boxes, we use the box, say the soil box first. We mount it on the shape table platter. It's equivalent to, post-mentioned structural specimen, so to speak, with the platter. So that the site covers that. But to film the box is equivalent to building a specimen into technical engineering. So that would be the cost of the research team, including let's say there is a foundation embedded in the soil, restructure. Now the other box, another box, the large rigid box, we have erected it only once in 2010 project back to back. One was the retaining wall I showed this morning, and the second one was the ridge piers with rocky foundation. So this box, the first time that we erected it, was very challenging. I remember the numbers. It took 19 days. The company that designed and built the box, they had 3 or 5 people from that company, plus 3 technicians from outside. So 19 days, we had also to rent a crane, because ours was not, the boom was not tall enough. And it took, I think, 5 days to dismantle. And the cost was the company lost quite a bit of money for building, erecting it. So they recuperated the money in the dismantling, and it costed $80,000 erecting and re-erecting. With the experience gained and the fact that now we have a model crane, hopefully we will not need to rent an outside crane. The lessons learned, and I think now we totally reduce this decline by maybe a factor 2, and the cost may be close to a factor 2 as well, $40,000. So because we never had a second case, and we never have included in our budget the operation of our site. A large budget item like this happens, we would talk when a second we can have something covered, the cost of erection and de-erection. This answers you. And then of course keeping the box would be covered by the research.
I think there will be perhaps a point of discussion with Joy if there could be a special call for geotechnical proposals using one of the boxes and the cost is shared between everyone. I think that would be very attractive to the community. So 1 year is you assemble the box and you have an entire year doing experiments with the box on, and then you remove it. So so many years. But it's good to talk to Joy about that.
It's a very good idea.
John, the question was for me, I think you have
That was a clarification saying that maybe Joy could do a special call for proposals and try to get several together and have a cost share. So just another idea on how to.
Yeah.
So regarding working together, Ahmed did the project with the cut and cover tunnel, and basically went around to many different committees, went to DFI as an organization and said, we have this shake table that's here, you as a community want to come and do tests. So DFI said, oh, we just sponsored a project, Amy Serrato, looking at theoretically coming up with assessment response. A bunch of our companies will chip in money to come and install some there and do that. So he was kind of tangentially involved with that set of tests because he kind of told them to come and do it, but Amy Serrato came and got funding, and so that it didn't really maybe save any money for Serrato, but there was another project there. They got a lot of visibility using a lot of papers that came on after it. That's one example. Just trying to go to the community saying, look, we have this opportunity. Somebody's going to raise their hand. I think if there was like a bio-geo application, I'm sure this is a hot topic.
Has this program ever discussed any more extreme geotechnical phenomena like fault rupture?
Well, have you heard of anybody doing fault rupture proposals?
No, but the idea was discussed. Normally, it's Cornell, they have a device that it can dislocate by the producer discontinuity for a pylon, for a pipe underground. And here we will need build a box. You can also dislocate it. Half of the box could be on the reaction axle, half on the path. The idea was discussed, but never a proposal written on this topic.
Yeah, I think having stuff off of the shake table and on the shake table, probably have to do some simulations to make sure that everything's going to behave well so nothing gets hurt. But we've done, I showed one picture there of the MSC bridge abutment on our small shake table here on campus. It wasn't big enough to accommodate both sides of the bridge, so we put one side on the bridge and then a sliding platform off the bridge. So it's not required, and you saw the picture from Professor Streppo going off to the side. So it's possible to have things not just confined to the geometry.
Can you just let us know which kind of budget items responsibility of the PI and which one is responsibility of the facility?
Joel, do you want to answer that? The question was what budget items are for the PI and which ones are for the site? Maybe in general.
So, yeah, so for the PI, it's the construction of the specimen and the demolition. The site has to install the specimen on the flattened instrument according to the desires of the researchers, as long as it's not very unique instrumentation that we don't have. In this case, the research team will have to bring the instrumentation and data acquisition system to run in parallel with ours. And then the researchers are in charge of the demolition of the specimen, which often is kind of neglected until the last minute. And there are often some surprises that the cost is much higher than what the research team imagined. And then we have to run the test for you, give you the data. So that's kind of, it's really simple. And then, yeah, there is something else. And, so in building your specimen, you would often hire a contractor. And you cannot have just a contractor arriving at the site and work in isolation without interfacing with our staff. So for safety reasons, there is a need to interface with our staff, at the site, whether you want it or not. And our staff works towards the construction of your specimen, then you have to pay our staff on a recharge basis. And also when our staff is the only one who can operate the machine at the site, the crane, use it, the boom lift, and so on. And we also, because these machines do not belong to the NHERI site, they've been paid and they are maintained by the department. So we have to also charge the use of these equipment. And when you write your proposal, it's very important to discuss with our team, mainly our technician, Uro Shapula. With their experience, they could give you some good estimation on how many hours of staff time and use of machines we would propose.
Yeah, so I think the typical timeline that happens is you come up with the idea, you write the proposal and everything. Now there's no deadline anymore. There used to be deadlines. So people would put something together really quickly and they would come in at the deadline, and maybe they got funded. And perhaps they didn't contact the site to explain the things that they were doing to make sure that it was feasible. But now there's no deadline to submit. So in that case, it's good. Once you've you have the idea, you have some drawings, you have some plans on the sequence of tests that you want to run, to reach out to the site, to one of the different co-PIs on the site, or directly to Joel, and he can direct you to somebody else, to say, here's my idea for the proposal. We need to keep that confidential, so we're not going to do anything after that because it's your intellectual property. But we can say, oh, we don't have, you're proposing to use 1,000 sensors, we have 500. Or it's going to be very risky if you do something like this, it could damage the device. So those sorts of pieces of advice will not only make sure that the project is successful, but it may actually help your chances when you're waiting for control. It look more feasible. Does that make sense? So, and as one of the components for a project to use the site, you have to have a letter from Joel as and I think the letter can't really say anything. It just says we commit to help your project as described. Project description, as you've seen from previous projects. So, and I think Joel said if you really are in a rush or something, then we'll still be supportive. But the more contact and interaction you have, the better.
Can I ask a question about an earlier talk?
Yep.
This is for Adam, for the design.
Yeah.
So today you mentioned about the data sharing, data talk, but in terms of like developing proposal using safe design resources, can you go over that?
I'm glad you brought that up. That's a great idea. All the data is obviously available, and you're always doing work to prepare for a proposal. So doing some preliminary analysis using data that's already available that kind of shows something is viable is completely acceptable and really looks good, I think, when a proposal gets reviewed. I want to add on though, also, I know we're here talking about experimental facilities, but you could write a proposal that actually has no experiments, it's just going to reuse data. And so don't only think that you need to propose to NSF to do experimental work and use NHERI resources. Or maybe you're going to do one experiment, but it's coupled with some analyses of previous experiments. So bringing old data with new data that maybe fills a gap with the old data, also I think will review well. And then access to the high performance computing, all that stuff that is, if I wasn't clear, that's free to everyone. Even if you're doing as Stefan told you the secret, non-NHERI work, you know, as long as it's natural hazards related, the resources have been put there to make these resources available to you, so the funds have been put together. So yes, we're here to support you.
Oh, you brought this up. Actually, one of the questions we were discussing is for simulation data.
Yeah.
Like, what's the criteria? What fits design safe?
These resources that Helen is talking about now, is my research team has the high performance computing resources offered by Texas by TAC. It's fantastic.
Thanks, Joel. So your comment about, there was a question here before that I don't think you heard, Joel. Simulation data, what are the requirements for publishing or reusing or?
What's considered relevant to design safe?
So I think sharing and publishing simulation data is kind of the new frontier for us, right? We're still kind of evolving what is appropriate, right? So I like to think of definitely the input models that go into the simulation. It's great if you have the output. Sometimes the output is so voluminous that maybe you want to be selective about what output you publish. Now, I don't want to scare anybody about size, because we have, hey, it's Texas. We've got lots of, everything's big in Texas, right? Including our data storage. So if you need significant storage, we're here to support you. But I also think the more voluminous your data are, the more you have to think about how are people going to find within that structure the data. So for instance, you know, we published a data set of several thousand processed earthquake ground motions from Texas due to induced seismicity. Well, we actually published it with the Jupyter Notebook that allows you to search the database so that you're not just scrolling through files and folders to figure out which motions you might want. So I think as the data get bigger, you need to think about, you know, how can people make use of that data. But I think anything that you believe someone could make use of in another way is what we'd love for you to publish. But it's still new on people's minds. I think the simulation people haven't thought so much about what does it mean to share. In fact, we've talked about creating a working group and have some workshops with people doing simulation, trying to say, what do we think are the best practices for publishing simulation? Stefan, yes.
The other thing that we were discussing is what if the simulation data is also performed or gained with design safe resources, but it's not strictly hazard related stuff, it's in fundamental scope.
You know, I'm not going to not take your data. And hey, soil is a natural material, so I'm always like, geotech is natural hazards no matter what. But, you know, if it's civil engineering related, and if you think it fits into design safe, because I mean, the fact is there are other data repositories out there that you could consider, but if you know like all your other data is in design safe, and you feel like the community knows about design safe, so you want to cite data that's in design safe, then we don't have any problems with that.
Yeah, I'll add one thing too about like.
Oh wait, hold on, Joel.
I'll add just about like the size of the data, right? A lot of simulation data involves just huge amounts of information. The people at TAC are used to working like with astrophysicists. So they think that when we think it's a lot of data, that it's super cute. They're like, oh my God, that's so cute. They think that's a lot of data. I just asked, you know, we're gonna have a database that's like a single database file that's 9 terabytes. Is that okay? They're like, that's nothing. What are you talking about? So seriously, what we think is a lot of data is not a lot of data for them, right? Just, you can do it. It's not gonna be a problem, I think. In terms of storage, right? RAM
Yeah,
maybe
yeah.
another thing.
Tim Cockrell told me that exact same thing.
Yeah, Tim's the one who told me that too. Natural hazard speaking, come on.
Joel, you wanted to say something?
I have a question for Adam
Oh.
about, so it's my understanding that this data right was moved to the NHERI data depot. And have you guys had discussions about the after NHERI? What would happen to the data depot after NHERI? Safety be moved along?
So we have a commitment, if there is a new awardee after us, that we will transition that data to another awardee. If there is no other awardee, you know, TAC has been around now for 20+ years, and we have the commitment of the director to maintain the data available. Now the problem is, you know, the nice user interface. If we don't have funding, we might have the data available. The nice user interface using the web portal may go away. But I'll be honest, my strategy, as you notice, DesignSafe does not have the NHERI name in it. So if NHERI ends, perhaps DesignSafe will continue. And I do think when we consider that NSF has invested 20+ years between NIS and NHERI and data, it would be hard for them to just completely dissolve the fact that there's a data repository, whether it goes to another awardee or stays at TAC or in Texas. I have a question in the room. Okay.
So, there's so many research on natural hazard outside of NSF. You have to try to reach out to PIs from other sponsors to add data.
So yeah, we through the Converge group, that's part of NHERI, which involves social scientists too, so we're getting social science data. I think the earth science data is a different ball game, but I'll tell you, this is something really exciting happened to us this summer. Is Maria was reading the New York Times, and they were talking about there was a megastorm, the new big one for California is the megastorms of California, which you just experienced this week apparently, right? And so she's like, oh, wait, and then she saw a data, put their atmospheric weather simulation data they published on DesignSafe. We knew nothing about it. Like they use DesignSafe. So here are examples that people are seeing DesignSafe as the place to put natural hazards data. But we are reaching out to other communities, but I do think that other communities sometimes feel, depending on what type of data they have, they've used other data repositories. But I do think we're starting to see more diverse data in our data repository.
For example, I know there's more than 50 UTC
UTC, University Transportation.
And they have requirements for their data, and it was struggling which kind of
right. Are they natural hazards, or is it more just all general transportation engineering? Yeah. So the challenge always is when you have a broader community like that, like we could take the natural hazards side of things. The question is, and this goes back to what we were just talking about, like general soil mechanics, does that count as natural hazards? Like does corrosion of reinforced concrete bridges count? Well, yeah, sure, that's climate change, right? So I don't know where the boundary is, but if you have contacts that would help, that we could reach out to, or if you hear people are having these struggles, so come talk to me about the appropriateness, because we have the space. As long as we're using resources that have already, and capabilities that already exist, we have no problem supporting other aligned research communities. Sure, love it.
So for data reuse, it's always an end product, right? So I did the test, I uploaded, someone else maybe have access later on after I upload to do. But sometimes if as a user, I may be limited to the instrumentation that you have already in the building, so maybe I'm not able to do something I want to do because there's no data for it. Did you think of this a problem before, like maybe have some outreach to community before you test to propose maybe additional instrumentation?
I think that's a question for the experimental facilities, right? Yeah, that's the idea of the payloads, right? And I think that's a wonderful idea. Because if you've got this big building and someone could just put a few extra sensors and try and study some mechanism of energy dissipation, for instance, it's a little investment for a big payoff. So I'm assuming, John, you guys consider that.
Yeah, so that's part of our user support. We're not going to design your instrumentation plan for you, but if you share your instrumentation plan with us and we see maybe if you put a measurement there, you're going to be able to.
I'm saying if this is happening in maybe 3 months, and there's a way that if I share the existing plan sensor and get feedback from Rob Watkins on additional sensors or
It's more promoting that this experiment is going to happen. Do you have an idea of additional instrumentation to study a specific thing? Right.
I think it's come up in the past. Joel, the question was whether if you share your instrumentation plan with other people and allow other people to add their own sensors in that essence.
Yeah, and we often have a search team, the instrumentation plan, and also about the payload of the, like for example, the transport, there's a lot of discussions if there are any proposed to the research team can install sensors. Then there is also the issue of additional sensors are brought in, interfere with vision of other things and not really bring new data. It's just redundant data, and we have some time to say no, we just introduce more delay, and then the project team has got the scope of this, and just to have more sensors that provide no redundant data. So it's a balancing act. I think it's always very good to try to open the gate for this big old project, new type of sensors, if they bring new information.
I wanted to add one thing that I forgot to mention during my talk, so I'm going to take this opportunity to say it now. Because when you're doing experimental work, and this is what I thought you were going to ask, is there's this idea of, oh, the experiment's over, so I should upload the data and publish it, okay, moving on. For what I've done with my research group to more strategically make sure I'm using design safe is when my students publish a paper, they publish a data set that we cite in the paper that has the scripts, the data, the output, the inputs, etc. And that's one way us as faculty members can kind of get into that habit of, okay, I submitted the paper for review, here's the data set, and that way you're pushing those things forward. And because now we have versioning, if during the review they say, hey, did you analyze this? You could just publish a version 2 during the review process.
Well, I just realized that I need to depart from my son's holiday recital, but I think this is a great discussion. We have another Q&A session tomorrow, so I will continue that, as well as continuing the discussion over dinner, which is available here on the patio. It may be chilly, so I think the best is to probably get the food and come back into here. And yeah, I'd like to thank you all for coming, and it's been a great workshop so far. I'd like to thank all the speakers, everybody who's been traveling out here. We're going to thank you again tomorrow. So. Thank you, Joel. We get our structure.
Oh, great. On a good day or like a profit?
Kind of, yeah. Yeah, you could.
Yeah, exactly. That's what I was going to say. Oh, you better go. out, right?
Yeah. Thank you for
Oh,
coming.
no problem, it's great.
Strength of soil.
It really helps us to promote what we're doing
So
too.
what really matters is
We
shear
can
stress
talk
divided.
more.
Tomorrow, yes, yes.
Good luck on your recital, Colonel.
Thank you.
Oh, yeah, sure.
Yeah, that was awesome.
Good luck on your recital.
Yeah, they're up for.
The CS, for a constant CSR,
It
unfortunately.
was a nice, yeah, it's on the other side.
I hear a lot of walk.
It was nice walking here
The shear stress is
this morning. Now I'm like, oh my God, I'm gonna freeze.
And there's always.
It's dimensional.
That's a nice.
Yeah, and CSR.
Yeah,
is
yeah.
The principal stress direction doesn't change.
I think it's like.
Yeah. Yeah, it was
It
like
does
eight,
change.
well, originally I said,
Simple
John,
shear
come on,
principal
you
stresses
consider
are
what you want to do, because I want to talk about the
So the material is
student, like the Oregon State.
you get these.
And then I made my flavors rolls, and then I didn't think about that. I had said I wanted to do dinner, and I landed at 8 o'clock. I was like, oh, that's too late. But I was so worried about grading. Then I was glad I made a later flight, because I wanted to watch the World Cup game before I came over, so.
Yeah.
So yeah, but then I was staying, I don't know if I mentioned, I was staying till Saturday. My cousin was down there.
Because of the crystal structure.
Go down there.
It's also plasticity.
Oh, yeah, oh, Tijuana, I didn't know it was called, you never said it was called.
Teaches the local lingo.
Yeah, yeah, yeah. Yeah, almost basically there, yeah, yeah.
We're there from here. We're probably closer.
But, anyway.
Soil is the same way. It's anisotropic, it's particulate, it's not even continual. Well, I guess metal's not a continuum either if you look close on it. It always breaks down to some point. But, so this modeling is very simplistic, but actually,
I don't know.
anisotropic nature of the soil.
His brother is a geology
But you're right. I mean, even the basic vertical propagation stress directions.
In your calibration.
I'll end up on the.
See you tomorrow morning.
No, we're in LA.
You did, okay, I knew that.
The calibration is the same stress pattern.
Same stress
So we use the same.
Well, my husband's
Except for when you
from
have
the Bay Area, I'm from the East Coast, my brother lives in North Carolina now, my mom lives in Florida, so like we're all.
And the way the propagation is now too. So you match.
All my cousins,
So
I
that's
have a
when we
sister in
have
Riverside.
anisotropy.
A cousin, a couple cousins like in that area. Everybody's in LA except for I have two brothers.
Yeah.
But that's not possible.
Yeah, your brothers in Oakland. The rest are still like.
Yeah, but you
Figure out
can't.
like areas that cover 30
Sounds like LA, Riverside. Reverse of the LA, but yeah. So we have the right
Horizontal stress is the only thing. And you're not, they don't even think in terms of stress to they get trapped in this. Yeah, stress is really simple, it's fundamental. Probably the same as true structure like your hair, right? It's like axial load or bending moment.
We're gonna have this discussion about the data workflow.
In mechanics and like metal has the same. Then it's
How are you getting there?
So computational mechanics means tensors, like structural engineers, you just use building code.
Yeah, there's branch on the
That's what geotechnical.
Yeah.
But it moves. I mean, it's kind of